this video, we're going to talk about point-to-point communications in MPI. I don't want to waste any time because this video is going to be an exhaustive one and it's going to be a lengthy one as well. So let's jump right into point-to-point communications. So the most important takeaway from this video is that at the end of the day, point-to-point communications means that we try to communicate from one process with another process. That's what we want to do. And no matter how complicated sort of the syntax gets with all those different types of communications, different modes of communications, at the end of the day, it's going to be one process talking to another process in the form of sending and receiving messages. It's the most basic form, point-to-point communication in MPI, and it has this send and receive sort of mechanisms. So this is a very simple example. We have a simple example similar to this one. Let's jump right into the first one. It's a blocking send. Take a look at this one. This is the general form that how basically the standard presents. This is language independent. No matter it's Fortran or C, this is how this operation is constructed. So you need a buffer, that's an input. You need a count, how many elements you want to send. You need the data type. So this is the type. Also notice that this thing is not bytes. This is literal counting. Like I say 5 apples. Apple is the type that I have and 5 is the count. So this is also the same here. So we don't care about the data type when we are counting, because the data type is going to be the next sort of parameter. You need a destination, you need a tag to put a tag on your message. Later you can query that, or you can receive basically messages with a certain tag. And then you need a communicator. In which context are you communicating? So this is the C binding, MPI send. This is how it looks like. You have a new version, sort of is _C. Unfortunately, OpenMPI doesn't have this version, but if you happen to have the MPI library, that one supports this _C, and the only difference is that it supports with MPI count instead of int as the count. And MPI count as sort of an upper bound compared to integer, because our systems are getting bigger and we want to let's say send more and more counts of data, because integer, assuming that you have 4 bytes, it's going to be 32 bits. 1 bit is going to be for the sign, so it's going to be 2 to the power 31 minus 1. That's the count of basically messages that you can send. But MPI count presumably is probably double the size for 64-bit systems. Yeah, so it's going to be 2 to the power 63 minus 1, but I'm not sure. Presumably it's going to be double though. Okay. So you have so these 3 things, buffer, count, data type. This is the message that you want to send, and the rest of them, destination, tag, and communicator, is going to be basically the message envelope. So this is the context. So this is and the source is missing here, because the source is going to be implicitly inferred. When the process 0, for example, calls MPI send, it already knows implicitly that process 0 basically called that. So there we go. We're going to jump into message data. So the basic data that you have, for example, in C, it has sort of an equivalent in MPI. You can take a look at this sort of table. And it has a little bit of support for C++ data types, and for Fortran is there. We don't care about that. Here we don't have, this is the message envelope I was talking about. Basically, message envelope contains these 4 information: source, destination, tag, communicator. That's all the information you need. And here we don't have any important stuff. Let's jump into blocking receive as well. So this is how blocking receive looks like. It needs a buffer, count, data type, source, tag, come. To this far, basically, everything is similar to MPI send, but it has also a status parameter. And take a look at the status here. It says out, and this one is also out. What in and out means? In means basically you pass in the parameter there. These are the data that is going to be used by the MPI operation. And out means that basically the MPI operation is going to basically update that value for you. So buffer is going to be updated for you, of course, because it's a receive operation. And status is going to be also updated. That means that you're going to get some information. And that status basically contains information about that message envelope I talked about. So it has 3 fields. It has, I think, source, tag, and an error associated to that, if any error happens. So this is MPI receive, and you have the underscore C version. The only difference is that it supports MPI count. So these two things, the rest of them, okay. So receive supports some wildcards, and those wildcards are MPI any source and MPI any tag. So basically, you can put a receive a statement or a receive operation somewhere in your application that takes, for example, a message from any source or from any tag. And you might have guessed that, for example, MPI send must be very specific to which sort of process you want to send your information. But in the receiving side, we are saying that you can take information from any source or you can take information from any tag. So this means that MPI is sort of push-oriented, let's say, instead of pull-oriented. So this is something to basically not notice. This is the return status section. Let's see if something important is here. No, these things are not important. Okay, you can also get information. So the status object is an MPI object. We said that it has sort of source, tag, and error associated to that. You can directly query those things from the status. But sometimes, for example, you want to see the count of the message that you received, so you can use this sort of procedure. This is MPI get count. The binding for C is MPI get count. Of course, there's an underscore C version, which supports basically instead of integer, it supports MPI count. So this thing, you're going to pass in the status. You're going to pass in the data type, which is, this should be compatible with the receive statement that you have. And then you're going to pass in sort of a pointer. You're going to send address of sort of the count variable that you want to basically fill it with this procedure. So this procedure is going to update that count for you, and then you can basically query that and see how many elements were sort of transferred. So let's take a look at an example here. MPI, I think it was send old, yes. So in this very simple example, now this is basically to see how to use the syntax. We have a simple string, a const char star. It says I'm process 0 and I'm the king. The buffer is the length of this string plus 1 because it's null terminated. And then these things, we're not going to comment on them because we have seen them in previous video. So rank number 0 is going to copy the string into the buffer. And the buffer was previously allocated with proper size of the message, right? And it's going to send information. It's going to send buffer with this sort of count. The type is going to be MPI car, and it's going to send it to process number 1. This is going to be the tag, and this is going to be the communicator, the default communicator. And process number 1, on the other hand, is going to receive information, and it's going to print it. So you see that I put print statement immediately after the receive. That's because it is safe to do that, because MPI receive is also a blocking sort of operation. It means that when the sort of control returns to after this basically MPI receive, then you're safe to basically read whatever data which is written into the receive buffer. The same goes also for MPI send. When the controller basically comes back and returns from MPI send, you're safe to basically change the buffer and manipulate the content of the buffer. So let's go and MPI cc MPI send old, and we're going to say MPI run minus MP2, for example, and that's going to be a.out. And you see that the message was received, and that was I'm process 0 and I'm the king. So now you might be wondering, like, why do we want to send and receive information from one point to another point? Let's take a look at this presentation now. So one application is, for example, let's say you want to do some computationally, you want to compute a heat transfer in a rod, in a metallic rod, let's say. you decompose your domain, your rod into, let's say, some meaningful intervals, just like what you see here in this presentation. And then you assign each section to one process, like these bubbles you see around those things. So process number 0 is responsible for the first sort of computational cells, process number 1, and so on and so forth until, let's say, all the computational domain is covered with processors. Now, let's say you want to know at this specific location, at this specific computational cell, you want to know what is the driving force of heat transfer. What is the sort of temperature gradient in the direction of x. So assuming that you want to basically have, I cannot point here, let me just go out of this. Assuming that you're going to use, for example, a central scheme, you need information from this neighboring cell, the one after that, and the one before that. So the one after that is okay because it's in the jurisdiction of process number 1. But the one before that, it's in the jurisdiction of process 0. So you see the context, you see the application, right? So in this case, you need to send information from process 0 to process 1 so that process 1 can basically compute sort of the temperature gradient at that computational cell. And then we're going to see sort of what's going to happen. So this is the pattern that we were talking about. Process number 0 needs to send information. Process number 1 needs to receive information. And imagine that we are also right here at the end, right there. And we want to basically, so the same pattern, all I'm trying to say is that the same pattern can go from process number 0 to process number 1. That process number 0 receives information from process number 1, and process number 1 sends information to process number 0. So you need to make sure that these send and receives are basically called properly. Otherwise, you're going to hit something which is called as a deadlock. So you're going to wait basically forever. Your application is going to hang up. It's going to wait forever because there's no proper, let's say you send information, but you never basically call the corresponding receive operation for that. So you don't want that thing basically to happen. So instead, you can use something which is called send receive. We haven't talked about this, so let's go back and go further. As I said, MPI status get source. This is another sort of procedure that you can use to gain information from source. But you can get source directly from the status object. Simply you say status dot MPI source. That's going to be it. And then you have another one to get the tag. These are for ease of use, let's say. They don't have any significance to them. Passing MPI status ignore. Oh, this is something which I didn't comment probably. MPI send old. On the receiving side, we used MPI status ignore because let's say you don't care about those status information, those fields of sort of source tag or the error, you don't care about that. So you can use this sort of MPI status ignore, and that is sort of like a dummy thing, you know. So this is for that. Then we have blocking send receive. This is the subject that I was talking about right here. So you can combine sending and receiving both into one sort of operation. Let's take a look at it. It needs a buffer, it needs a count, it needs a type. So far similar to MPI send, it needs a destination, it needs a tag. And then right after the tag, it needs a receive buffer. The receive buffer can be different from the send buffer. This is important to notice. Receive count can be different from send count, and receive type can also be different from the send type. And then you have a source, you have receive tag. Tag should be different. And then you have the communicator, and then finally you have the status. And then in and out, you see that, you know, for example, which things are going to be written or are going to get updated by the operation. So this is how it looks in C and the _C version, which supports the MPI count, of course. These are not important. So this is another version of it. So what is this one? We haven't talked about semantics of MPI send and MPI receive. So MPI send is not going to return the control back to the process, for example, number 0, not after that you can safely basically manipulate the buffer. So right after the send operation is completed, which means that the send buffer is safe to be manipulated, then that is the time that the MPI send is going to return the control. And for that to happen, of course, there needs to be a corresponding receive sort of call. And but for send and receive, this both the name says send and receive, so you should not have this sort of idea in your mind that send happens first and receive happens next. So both send and receive are happening concurrently, as if, for example, sort of the caller starts to have like forks two threads, and one is responsible for the send operation, and one is responsible for the receive operation, and then finally it joins them basically. So this is sort of the semantics of send and receive. But it means that when send receive, MPI send receives, returns the control, you are safe to basically manipulate the send buffer, and you're also safe to read from the receive buffer. There's a variation called MPI send receive replace, which basically uses the same buffer. So as I said, the buffer here can be different. Send buffer can be different from the receive buffer. Where is it? From the receive buffer. But the replace variation basically uses one buffer to do both send and receive. So when this thing comes back, it means that the buffer is basically ready for you to be read. The information that somebody else, another process, sent it for you. As I said, these things, they don't exist. The variation with _C in OpenMPI. But if you happen to have the mpich library, then you have access to them. You have data type matching and data type conversion. This is probably, we're not going to comment too much on this one. Basically, the significance here is that when you're sending and receiving, the types must basically match. And this is, you can simplify it in 3 stages. Data is pulled out of the send buffer, and there's going to be a message assembled, and the message is going to be transferred from the sender to the receiver, and then the data on the receiver side is going to be pulled out from the message, and it's going to be disassembled to the receive buffer. There we go. These are Fortran examples. We don't care about them. Data conversion. Okay, MPI should be sort of supporting parallel communications across heterogeneous environments. What does it mean, heterogeneous environment? It means that if you have, like, I don't know, my computer, my laptop, another PC, you know, systems which are not exactly identical to each other. So it should operate on heterogeneous environments as well. Let's say one system is even little endian, the other one is big endian. So MPI, a good library should be in a way that it basically provides you portability to run your applications on heterogeneous environments. So there's going to be a type conversion, which is not going to happen because you're not going to change types from real to integer, for example. This is a Fortran example. But there might be representation conversions because, as I said, some systems might be little endian. The representation is different than the big endian ones. Or here the example is like hex floating point to IEEE floating point. MPI does not specify rules for these, and that is probably done by the implementations. We don't care about these stuff. Then we have communication modes. Okay, this is important actually. So we have talked about send and receive, MPI send and MPI receive. We said that those are blocking calls, but those two calls are basically something which is called as a standard communication mode. But we do have other sort of modes of communication. Another mode is basically the buffered one. We can actually go back to here maybe and talk about this. So standard generally is non-local. This is what it means. These are the communication modes. I basically summarize them here instead of going through the document. We're going to see that the document in a second. So the standard way of communication is generally non-local. What does it mean non-local? Locality depends on the involvement of other processes for an operation to complete. For a standard send operation, let's say MPI send, there has to be a receive operation which matches that send operation. And that is the only condition that basically the send operation can be completed. So that is why the standard operations are not local, or they are non-local. It's because they depend on another operation, on the other processes to basically get triggered or to get initialized or started so that these operations can be completed. The buffered mode is local, and the reason for that we're going to see in a second is because, for example, MPI bsend, when you're using buffered send operation, so you're going to have a buffer, and the process which calls MPI buffered send is gonna start copying the content of the buffer into the content of the message into that buffer that you allocated beforehand, and then after that copying is happening, then immediately it can return the call basically back to the execution line after the line of MPI bsend. So this is what it means. So it means that it means that it basically doesn't need the completion of buffered send doesn't need other processes to trigger or to do something. Synchronous is also non-local, and we're going to see what synchronous in a second means, but it basically means that it's going to basically wait so that a receiving call is basically started. And ready is going to assume it's also non-local. Both of them are non-local because they depend on the status of sort of other processes to do something for them to be able for them to be completed. And ready mode is basically means that it's going to assume that the send operation, the receive operation is already called and is waiting in the case of, for example, MPI rsend, which is the ready mode send. So this is the buffer mode. As we said, the buffer mode operation can be started whether or not a matching receive has been started. So it's going to, it doesn't depend on other processes to launch a matching receive. So this is the characteristics of a buffer mode of communication. Synchronous mode is going to be started whether or not a matching receive is started. But however, the send will complete successfully only and only if a matching receive is started. And the receive operation has started to receive the message sent by the synchronous send. So this is the significance of the synchronous mode. So the only way that the synchronous send is going to complete is that only a matching receive is started. And then we have the ready mode, which may be started only if the matching receive is already started. Otherwise, the operation is erroneous and its outcome is going to be undefined. So, and this is how these different modes of operation work. So we had MPI send, now we have MPI bsend. So B stands for buffer, S stands for synchronous, and R stands for ready. Now you know the difference. For example, B is the buffer. You're gonna have a separate buffer to copy the message into that buffer, and then you come back. It doesn't. It's local. Doesn't depend on other processes. Synchronous is going to be easy. It's going to start no matter you're having a matching receive, but it's going to complete only and only when you have a matching receive on other processes. And then ready, as we said, ready assumes that a receive has already started and starts to basically send the message as soon as possible. You see how it looks. I'm not going to comment on these because it's going to be quite similar to what we see. So now you know the principles, how they work behind the scenes. So we don't need to spend too much time on these things. So basically, you know that we have a variation of MPI bsend in C. We have a variation of MPI ssend for synchronous. And this is the rsend, the C bindings. I don't see anything important. Here probably is important. Ready send, the message is sent as soon as possible. Again, we are stressing on this fact that you need to learn these principles. Synchronous send, the sender sends a request to send message. The receiver stores this request. When a matching receive is started, now the receiver sends back a permission to send message, and the sender now sends the message. So the standard send can use the first protocol for short messages. It means that the send can basically start as soon as possible. And it can also use the second protocol for long messages. The buffered send, the sender copies the message into the buffer and then sends it with a non-blocking send. Okay. So semantics of point-to-point communication, we already talked about these stuff. So messages are not going to be overtaking, they're non-overtaking. So you can read these things yourself and you're going to understand them very easily. Fairness, there's no guarantee for fairness, handling of communications. Resource limitations, you can read these things by yourself. You're going to understand them quite easily. Then we have the subject of buffer allocation and usage. So I'm going to talk about, let's see if I have an example here. So let's take a look at this one, MPI get count. Oh, actually, I have used those things to get those information with get count, and also there's another variation called get elements X, which works with MPI count. Okay, we haven't run this example, but this is basically trying to send a huge amount of sort of integers. In this case, how much is that? This is 1 million. Yeah, 1 million integers with count and size of integers we want to send from process number 0 to process number 1. And then after we receive those things, we print sort of the status.mpi source. This, as I said, you can directly access a source and the tag. But if you want to see, for example, the number of elements, you can use MPI get elements X. Or you can use MPI get count as well. Both of them are valid. But elements X is for the cases that messages are big. And don't forget to free the buffers because these things are dynamically allocated with malloc. We can also take a look at it, actually, MPI CC, MPI get count, and MPI run minus MP2 and a.out. It says that it sends 1 million of integer elements and process number 1 receives those elements. The source is from 0, the tags is 42. These are the information in the status that you can query after that. And this is the count with that call to MPI get count or MPI get elements underscore X. What else do I have here? I have an example. Did we go over this send receive example? MPI send receive. This is the same sort of I'm the king, but this time we're going to use send and receive buffer. Oh, I haven't talked about this one. So here you can see I used MPI proc null. So MPI proc null is very, very useful. You can use it for sort of dummy sends and receives. Because sometimes, you know, when you're working with boundaries, then you don't need to actually send or receive some data. And this is sort of a placeholder or a sort of dummy, let's say, processor that you can use it as a destination or as a source in receive operations. And then we are using MPI receive. We can also try to run this thing, MPI CC, MPI send receive. And then we're going to say MPI run minus NP2 and a.out. The message received was I'm process 0 and I'm the king. And this is exactly as I said, the previous message that we had is in this MPI send alt. But this time we send it with send and receive operation. You saw that the send operation was meaningful, but the receive operation on process 0 was having sort of that dummy receive, which was MPI proc null. Okay, I kind of lost the thread. We were talking about, buffer allocation and usage. So that's this example. Now I remember MPI buffer. So if you want to, you remember that we talked about buffer send, ready send, synchronous send, and stuff like that. I have one example for a bsend because it might be a little bit more difficult compared to synchronous and ready, because for buffered you need to allocate the buffer beforehand. So if you want to use bsend, for example, then you need to sort of have a proper buffer for that. Let's take a look at this thing. Where is the MPI? Yeah, I was looking for this one. I couldn't find it. MPI buffer attach. So here we have our data is basically 10 integers. We take the data with malloc, with dynamically allocated, and then finally at the end we need to free that resource because it was dynamically allocated, and then you need to say MPI buffer attach, and this is sort of let's take a look at the syntax. What do you need? This is the com attach. By the way, you can have buffer allocation 1 per communicator, 1 per session. We haven't talked about these, so you don't worry about these stuff. But the one that we already talked about is 1 buffer per MPI process. So this thing is not important to us. The session attach is not important to us. The MPI buffer attach is important to us. It's going to take a buffer, that's our n, and then it's going to take a size for that buffer. So we're going to get the buffer for that. So that's, let's say, the size of 10 integers. And always, when you want to have communications also have some overhead. And whenever you want to assign some buffer, you always have to take care of those extra overhead, which is, for example, imposed to us by MPI bsend overhead. So that is why we add that extra element here. And this is the size. So this is, we send the malloc directly, call directly here as the buffer that we want, and this is the size. And then later, once you send with bsend and you receive with a regular normal blocking receive, then after that you need to make sure that you detach the buffer and you also free the resources that you have allocated. So this is quite important. Let's also MPI CC MPI buffer. MPI run, we can actually use the same MPI run. And you see that we sent, for example, these 10 integers from 0 to 9. And this was successful as well. So now you also know about MPI bsend, the buffer mode of the blocking send. Okay, these things are, this we already talked about. Detaching is sort of important to take care of stuff that you do. MPI session detach. As I said, we haven't talked about sessions and communicators. We don't care about them. This is the one that we already talked about in that example. Then you have flush. Probably we're not going to comment on this one as well because it's quite simple. If you read it, you're going to understand it quite easily. Yeah. But you know that the same combinations are going to be for communicator flush and session flush and MPI buffer flush. You have everything basically needed there. What do we have here? Are these important? No. Model implementation of buffer mode. Probably we don't care about this one. Okay, non-blocking communication. Now we reach to this section. Let's take a look at this. We said also communication types are blocking, the first section or the first sort of types that we have taken a look at. And usually it means that the call returns when the operation is complete. So that's the semantics. For example, what happens when the standard send is called? When does the sort of control comes back? When the call returns. Now we're going to go to the second sort of category or type of communications, which is going to be non-blocking, which the call, if the process calls that non-blocking operation, the call is going to return immediately. So the idea behind non-blocking communications is basically performance. So you sort of understood that with blocking communications, you have to always wait. You You have to wait for the communications to complete and then you proceed. But that is not something which is sort of good for performance sort of characteristics. So the idea of non-blocking communications is that you can, layer up like a hamburger. You can put computations as side by side or concurrently or as parallel as possible with communications. So you're going to have layer by layer communication and then communication. Just like similar to this example, sometimes you want to, for example, compute some stuff inside, but when you are, for example, computing stuff, then you can, if you use MPI send, the blocking send, it always sort of waits so that send operation is completed, and then it goes for the computations. While you can basically change that to iSend, this is sort of the non-blocking version of the send, which you can immediately return the call. So we haven't talked about this iSend and stuff, so let's go back. And so the idea is we're going to have better performance with non-blocking communications. And it also generally avoids deadlock conditions that we said. For example, for blocking sends, it has to be a matching receive, otherwise you're going to have a deadlock. Okay, we're going to pass these things. Similar to communication modes that we had for blocking stuff, that we had, for example, buffered mode, we had synchronous mode, we had ready mode. For non-blocking ones, we have also the same sort of stuff. The meaning is going to be the same. So now you know what basically, for example, buffered means. But the only difference for non-blocking communications is that the call returns immediately. So the process is immediately freed from that communication operation, and it can basically, it has the opportunity to do other stuff. It's not going to be idle doing basically, idling is basically stupid for a process. So that's the only difference. That's the only takeaway that you need to have. But the meanings is going to be exactly the same. What synchronous means in the context of blocking communication is exactly the same as non-blocking ones. So we're not going to comment on those stuff. Okay, so we have something new here. So here we have request objects. So let's take a look at sort of MPI iSend. So the I stands for immediate and incomplete. Immediate, it's because that the call returns immediately from that operation. And incomplete because since the call returns immediately, that it doesn't necessarily mean that the send operation, for example, is completed. It's not completed. So if it's not completed, then how am I going to know that the communication is already done? That is the subject of this sort of request objects. So with these request objects, you can then later query them with for example, wait mechanisms or test mechanisms to see whether the communication is already completed or not. But we are going a little bit ahead of ourselves. Let's take a look at MPI iSend. It's quite similar. MPI iSend, it needs buffer, count, data type, destination, tag, com. But the only difference is that it needs also a request. That is the subject that we were talking about. And you see that the request is also marked as out. And this means that this is something that the MPI iSend operation is going to update. And you see that request as a handle. So once something in the standard is called as a handle, it means that it's an internal sort of data structure in MPI library. It means that the implementation or the details are sort of private. They made private from the client or the user. You cannot basically see what exactly sort of a request data structure looks like. Or what exactly, for example, a communicator is also a handle. What exactly a communicator data structure looks like in an MPI library. But the only way that you can have access to them is indirectly through handles. And that's why you see a handle here. So you don't have directly access to request data structure, but you have a handle for that. So MPI ISIN, the C bindings. You have underscore C version. As I said, it supports MPI count. So far, you know the principles. The rest is basically, garbage. Now you know how MPI bsend, for example, looks. Very similar to the blocking versions, but you have an extra request there. It's a sort of a handle. Then we have the synchronous one. Then we have the ready mode one. You already know all the meanings of these. The only difference, as I said, is that the call returns immediately. The meanings of ready synchronous buffer, you already know them. This is MPI I receive. Again, the meaning is quite obvious. The call returns immediately, but it doesn't necessarily mean that the receive buffer is sort of safe to be read. Or when I say MPI I send, you immediately know that after the call returns, it is not safe to change the buffer, the send buffer, because you don't know whether the send operation is completed or not. Then we have MPI send receive, the same meaning as send receive we had for blocking version. Send receive replace, the same meaning as sort of blocking version, but this one is for non-blocking one, which the control returns immediately. So now communication completion. How do I know that this communication is completed or finished? I need to query that with MPI wait and MPI test. So MPI wait is sort of a blocking call. Whenever a process says MPI wait, it basically waits, similar to the blocking version. It waits up until to the point that it makes sure that the send buffer, for example, if you use it after MPI I send, you use MPI wait, it makes sure that the send buffer is safe to be written again or to be reused again. So it's a blocking sort of call, MPI wait. And it needs two things. It needs the request. If you remember, the request was sort of an out field for MPI I send. So you pass in the request here, and you see the request is marked as in out. So this means that there is, it can be at some sort of scenarios, it's going to take the information and use the information. And sometimes it's going to update that information on the same sort of variable. So in this case, request is an in-out sort of handle, that it could be used, the information could be used inside the operation, and it could be also overwritten by the operation. And then status is only out because it's going to give you the status, those fields that we already talked about. If you're not interested in the status, you can use MPI status ignore. So this is the C sort of syntax. You're going to pass in a pointer for your request, the address of your request, and then you're going to send the address of your status as well. Then we have MPI test. The only difference that MPI test has with respect to MPI wait is that this one is not a blocking call. It basically returns immediately, but it has a flag which is marked as out. It's going to be modified or updated with this operation or with this procedure. And this flag is going to be true if the operation is completed. So if I say MPI I send, and then immediately after that, I query with MPI test with the flag, and then I can say if the flag is true, then I know that the send is completed. And if the send is completed, it means that I can reuse the send buffer. So that's the syntax for MPI send. I think we can now take a look at, I think I had an example, MPI I send, yes. So again, the same example, that a string that we have seen a couple of times already, but this time we're gonna send it with I send. We hand in a request sort of handle. That request, we created it up there. That's an MPI object. And we pass in that request into this MPI test. We pass in a flag, which we already set it here. It's an integer. And we have the MPI status ignore. And then we check immediately if the flag send operation is completed. Otherwise, we say send operation is not completed yet. And whenever we say MPI wait, we make sure that send is going to complete. Or at least we're going to wait for that. Then we have MPI I receive on process number 1. And then we're going to make sure that we have this MPI wait call. And after this statement, so you see that this example is very probably stupid, because the idea of non-blocking communications is that after you have a communication, you can have a layer, a huge layer, or let's say not a huge, a layer of computation. But here we don't have any computation. We're not doing anything but waiting. But this is only to, as I said, you get the principles. This is only the syntax, how it looks and how it works. Then after this wait call, we are 100% sure that the message is safely received in the received buffer, and then we can read the buffer basically. So let's go with MPI CC and MPI ISend. Whoops. And let's go with MPI run. And it says send operation completed in that case, because immediately we tested after MPI ISend. Usually this shouldn't be the case, but it happened because our message was quite sort of a small. And this is the message, of course. Okay, let's jump back. And then we have MPI request free. Okay, we're gonna see these stuff when we talk about. Okay, let's not comment on this yet. Let's not comment on this yet. Semantics of non-blocking communication. Again, we already talked about these semantics. The order, you know. It says non-blocking communications operations are ordered according to the execution order of the call to initiate the communication. They're non-overtaking. Yeah, we already know all these stuff. The progression. Multiple completions. This is also a case, for example, you know, you already know that when I talk about MPI wait any, it's going to be waiting for any sort of process, any single non-blocking process. When we talk about wait all, it means that, you know, a collection of sort of non-blocking communication. So that's why I say when you get the principles, you don't need to worry about this stuff. So you have MPI wait any. That's the C binding. You know, you have MPI test any, similar to MPI test and MPI wait. As I said, these are very easy to understand. You can figure them out. MPI wait all, we talked about it already. MPI test all, we talked about it already. Wait some, again, you can read these and understand it quite easily. But these are basically, the principle is that you're going to wait. But there's a context. Wait some. You're going to wait for some of those non-blocking communications. Just read them and you're going to understand them quite easily. Okay. This is non-destructive test of a status. Probably this is also not that important for us. Let's not talk about this. Let's not comment on this. Let's go further. Okay, we reached probe and cancel, but I think I should have an example here. Do I have an example? MPI get count, MPI ISend. Probably not. Let's go back here. So probe and iProbe, again, you know, these variations, you already know what they mean. When we put either, it means immediate, incomplete. The controller is going to come back immediately. So cancel, you know, MPI cancel is quite obvious. It's for pending communications, which means that they are non sort of blocking. You can cancel them, but it's sort of, I think it's yeah, it is deprecated. Canceling a send request by calling MPI cancel is deprecated, so probably we're not going to spend too much time on this one. MPI probe is basically, you can probe, as the name suggests, you can probe messages without receiving them. So you can gain information on the messages that are flying around without receiving them. So you can know. Let's see what things they have. For example, this is MPI iProbe. It needs a source that's an in. You need to provide that source. You need a tag. You need to provide it. You need a communicator. You need to provide it. You need a flag that's going to be modified by MPI iProbe. You need a status that's going to be modified by MPI iProbe as well. That's the status object. So it says MPI iProbe returns flag true if there is a message that can be received and that matches the pattern specified by the arguments of source, tag, and com. So you pass in the source, tag, and com, and if any message sort of matches with these information from a specific source with a specific tag and inside a specific communicator, then you're gonna get this sort of flag for being true. So of course this is not a non-blocking version. This is the blocking version. It needs a source, tag, com, status. It doesn't need that flag. That flag is basically only because you can query that afterwards to check whether, if it's true, it means that you have the corresponding message. If it's not true, it means that you didn't find that message basically. But the blocking version basically doesn't need that flag. Again, probing basically means that you can probe messages without receiving them, as the name suggests. So these are some examples for that. I think I finished all my examples in terms of the code that we have, because I haven't prepared sort of other stuff. But there's one more topic that is important for us to know about, and that is the mprobe. You can also read it, what it means. It basically has a message handle. Handle, again, you know that what handle means. It's a internal representation or internal data structure. Again, you have mreceive for those messages, you know. I am received. This you can basically understand what the meaning means. The cancel, that procedure, what it basically does, it takes only request. That's an in. And the cancel also is sort of a local operation. It doesn't need other things. So it returns immediately, possibly before the communication is actually even canceled. So these things, you know the context, what it means, right? So again, different things here. MPI test canceled. You can read these for yourself. Okay, this is the last thing, which is probably important for us. It's quite a lengthy video already. I'm going to comment a little bit on this one, and then we're going to wrap this video up. So persistent communication is sort of the last type of, you can put a star here as well, because the call returns immediately, but there's a mechanism to basically activate and make them deactive those calls. And then we already talked about this one. Now you can have a different communication pattern with non-blocking, the simple sort of computational problem that we had. Now we can use MPI iSend and iReceive patterns, or you can switch it up with iSend receive on proc 1 and proc 0, or you can have, for example, in this case, because these information is going to be quite the same, because you want to pass around, for example, a temperature. So the temperature, if it's double, for example, it's going to be the same. So you can use the same buffer. So you can basically use this variation of iSend receive replace as well. You remember, replace means that you can use the same buffer for send and receive operations. We are done with that. This was the example with blocking communication. This was the example with non-blocking. And finally, now we want to go to persistent communication. What does it mean? Often, a communication with the same argument list, with the exception of the buffer contents, is repeatedly executed within the inner loop. So you have an inner loop of sort of communication. You're using all the same argument lists, but only the buffer is possibly changing. So in these scenarios, you can use something which is called as persistent communication. In such a situation, it may be possible to optimize the communication by binding the list of communication arguments to a persistent communication request once, and then you can repeatedly use it to start and complete operations. That is basically the idea behind persistent communications. That means that if the argument list is more or less the same, the buffer is possibly changing, and you want to communicate over and over, then you can optimize your communication by a persistent communication. Do I have... yeah, I do have one last example I forgot. I have a persistent sort of communication here. Let's go further. So the idea is that the version of the operation is MPI send init. You're going to initialize it, and it takes buffer count data type, destination tag com, and it takes also a request. It is quite similar to MPI isend because it takes exactly the same arguments, and you see in and out for everything. The request is an out. This is the C binding. It has an underscore C in MPitch. You have different modes of it. You can use persistent buffered mode communication. You can use persistent, I don't know, synchronous mode, or you can use persistent ready mode. You know what exactly the meaning of those things are because you know the principles now. You can have a receive init. That's for initialization of the receive, so persistent receive operation. The actual sort of process starts when you call this MPI start, and that gets a request, and you know that it takes it as an in and out argument. We're going to see the example in a second. And start all, you know what the meaning is if you know what the start means. Okay, and that's it. That's the end of chapter 3. So let's jump into this example, MPI persistent. Okay, again, you basically have a request, you have a status, process number 0, has a buffer. I said we use it for when we have an inner loop for communication, but this is a very simple one. We only do it once. So we have a buffer which is filled up with 42 on process number 0, and it initializes the persistent operation with MPI send init. And then it tries, this is actually when the operation starts with MPI start request, and then it calls MPI wait to make sure that the operation is going to complete, the send operation is going to complete. And it also needs to free that request. It's going to pass in that request for it. This is the subject of this section, which we basically passed so fast. I think it was this MPI request free was happening before. MPI request free. I think we have seen it before, but it seems like this PDF reader cannot find it. Okay, but anyways, this I think I skipped it because we haven't talked about the persistent communication, but now you know that you need to free the request. And then on the receiving end, you need to initialize the receiving. And then this is actually when the receiving starts to happen. And this is to make sure that the receiving basically happens and it completes. So after you say MPI start, it's more or less similar to a normal blocking MPI send. This is what it happens behind the scenes. And then after the MPI wait, you are sure that the receive buffer is safe to be read, and then you print the information from the buffer, and then finally you don't forget to free the request that you allocated here. Okay, there we go. This was a very lengthy and exhaustive video, but I hope you learned something from this video, and hope to see you in the next one.